Let's go on a little journey. It's one that starts right in your kitchen and ends up supplying clean water to an entire city. And you know what? It all picks off with a super simple science experiment you've probably done 1,000 times without even realizing it.
Seriously, think about it. You stir in 1 spoonful of sugar and poof, it disappears. You add a second and it's gone too. But then eventually you hit this limit. You hit a point where the sugar just sinks to the bottom, no matter how much you stir it. So what's really going on there? Well, let's dive in.
All right, here's our game plan. We're going to start with that full cup of tea. Then we'll figure out what that limit actually is scientifically. We'll see how a little heat can completely change the rules, and then, this is the cool part, we'll apply all of this to a massive, real-world challenge, getting pure, clean drinking water right to our homes. Okay, first things first. Let's get our language right. That moment when your tea just can't take any more sugar, well, that has a proper scientific name. It's all about knowing when a solution has officially had enough. So, you've got two main states here, saturated and unsaturated. An unsaturated solution is like that first spoonful of sugar in your tea. There's still plenty of room for more to dissolve. But a saturated solution, that's at its absolute max. It's full. It literally cannot dissolve one more grain of sugar at that temperature.
So, to put it really simply, unsaturated means there's room to spare, while saturated means you've hit the wall. But, and this is the important part, that wall isn't permanent. You see that little hint there about temperature? If you want to dissolve more, you've got to change the conditions.
And that brings us to this third, really cool but totally unstable state, the supersaturated solution. This thing is like a magic trick. You can actually trick a solution into holding way more stuff than it's supposed to, usually by heating it up and then cooling it down very carefully. But it's on a knife's edge. Just one little tap can make all that extra stuff dramatically crash out of the solution all at once.
Okay, so we know a solution can get full, but full is a little vague for science, right? We need a number. We need a way to measure that limit precisely. So let's get into how we actually define that.
Right. This is the big question, isn't it? We need a way to quantify that maximum amount so we can compare different things under different conditions. And lucky for us, science has a word for that. And that word is solubility. This is the official measurement, and it's always defined by three key things: the maximum amount of the thing you're dissolving, a standard amount of the liquid you're dissolving it in, which is usually 100 grams, and crucially, a very specific temperature. You change any one of those three variables, and the solubility changes too.
And here's a perfect real-world example. At about room temperature, 100 grams of water, that's roughly half a cup, can dissolve exactly 36 grams of regular table salt. If you try to add 37 grams, that last gram is just going to sit at the bottom, staring at you. The solution is now officially saturated.
But what if we crank up the heat? We already hinted that temperature is kind of the secret weapon here, especially for dissolving solids. So let's look at some actual data and see how this all plays out. Okay, check this out. A student named Suda gathered all this data for 4 different salts. We'll just call them X, Y, Z, and T. This table shows us their solubility at 5 different temperatures. And don't worry about the Kelvin scale. It's just another way of measuring temperature. The key thing to notice is that as the temperature goes up, pretty much all the numbers go up too. All right, let's play detective for a second. Let's just pick one temperature. How about 323 Kelvin? That's about 50 degrees Celsius. At that exact temperature, which salt can you dissolve the most of, and which one the least? So if we scan right down that 323K column, the biggest number we see is 42 grams, and that belongs to salt T. The smallest number in that same column? That's 34 grams for salt Z. So it just goes to show you, even at the exact same temperature, different substances can have wildly different solubilities. Okay, now for a different kind of question. Instead of just looking at a snapshot in time, let's look at the overall trend. Which one of these salts seems to care the least that the temperature is changing? Yeah, if you look back at that table, salt Y is, well, it's the odd one out. Check out its row. As the temperature skyrockets, its solubility barely budges, just creeping up from 43 to 50 grams. Now compare that to salt X, which just explodes from 22 all the way to 109. It's pretty clear that salt Y is the one that's least affected by the heat. Okay, so this is all really interesting kitchen chemistry, but why does it actually matter? Well,
it turns out the science of solutions and separating mixtures is, and I'm not exaggerating here, absolutely essential for our survival. You see, the water in our rivers and lakes is actually a super complex mixture. It's got dissolved salts, sure, but it also has all sorts of other stuff floating around. Dirt, sand, and the really dangerous things, harmful bacteria. We can't just pump that stuff directly into our taps. It has to be purified first.
And that whole purification process, it's basically a giant real-world application of everything we've just been talking about. It's a journey with a bunch of critical steps, all designed to separate the pure water from everything else.
And here's a simplified look at that journey. The water starts out in a reservoir and then gets sent through a series of massive tanks. Each tank represents a different stage in a really complex separation process, all with one goal: to get pure H2O before it ever reaches your house. The whole thing involves several key stages. We're going to focus on the big three: sedimentation, which is where the heavy gunk drops out, filtration to catch all the finer particles, and finally chlorination, which is the disinfection step before it gets sent out. So let's break that down. First up, sedimentation. Here, we basically just let gravity do the heavy lifting. All the heavy stuff like sand and grit just sinks to the bottom. Simple. Next, filtration acts like a giant superfine sieve, using layers of sand and gravel to trap much smaller particles. But honestly, the most critical step, the one that saves lives, is the last one: chlorination. This is what kills the invisible threats, the bacteria and pathogens that make the water truly safe for us to drink.
And that really brings everything full circle, doesn't it? The same basic science we see when we dissolve sugar in our tea is what allows us, on a massive industrial scale, to separate pure water from all its impurities. It's what ensures public health for millions and millions of people every single day.
You know, we've focused on purifying water, but think about it. What else in our world depends on separating mixtures? From the coffee you drink in the morning, to the gasoline that powers your car, to the very air we breathe, this science is absolutely everywhere. So, the next time you pour a clear glass of water, maybe just take a second and think about the incredible scientific journey it took to get to you. Thanks for joining me.